All right, week 7, chapter 17. So this chapter is mostly about carbon, and what we know about carbon already is that it's in group 14 of the periodic table. That's going to determine much of what we see because of its preference for 4 bonds. Probably takes several videos to finish this chapter because it's a big one. It's actually the chapter based on the PhD that I got from Mizzou. And it's really just about understanding hydrocarbons first and then understanding the polar groups, the functional groups last. Learning about how to name hydrocarbons, learning how to recognize carbon attached to different oxygen-based and nitrogen-based functional groups in their most generic kind of form. And then maybe that'll help us recognize the same ideas in drug molecules later on. So carbon comes from the Latin word coal, or carbo. We know that in its most stable form, it has 6 protons, 6 neutrons, and 6 electrons. We also know that it has 4 valence electrons, being in group 4, at least Roman numeral 4, or group 14, using that ones place as a representation of valence electrons, very important in the last several chapters. It is the 15th most abundant element in the Earth's crust, and it is second most abundant in our body, based on mass, oxygen being the highest. When it comes to carbon structures, the reason this chapter is its own course 2 years removed from this one is because carbon can do so many things. And that's what makes the human body very intricate and complex, because carbon atoms can do lots of different things in lots of different tissues, so to speak. Carbon also has the ability to catenate. Catenate is the ability to bond to itself over and over and over again and still be as strong as the original first bond. The only atom that's even close to being able to catenate in this kind of pattern would be maybe a sulfur or phosphorus or nitrogen, P4S8 or even N3 negative. Those are the kinds of molecules that are larger groups of atoms, but carbon can be millions, trillions upon trillions of atoms in a row in all 3 dimensions, so to speak. And that's what makes it so unique to any other atom on the periodic table. Since this is intro chem, we're going to focus mostly on chains and then branch chains a little bit. Carbon can make cubes. We don't have to worry about naming any of those. Can also make rings, and we're not going to have to worry about naming any of those. We're just going to do the basics in a separate video with linear chains and branch chains. Since organic chemistry is the chemistry of carbon specifically, this is what we're going to find with a lot of our petroleum sources. So a lot of what you hear on the news about fossil fuels comes from organic chemistry in its most basic sense. We'll talk about where to find those kinds of ideas here in a minute. But currently there's about 9 million organic compounds. That's about 90% of all known substances. So in a way, especially for me, with this being the area of my PhD, it's kind of sad to teach you organic chemistry in one chapter when it accounts for 90% of everything. But it is very specific to carbon and what carbon can do and how carbon can change. And that's why we teach it in upper level chemistry classes in more detail. We spend the rest of the semester really dealing with inorganic chemistry, which would be non-carbon containing atoms, which would be the rocks and the dirt of the earth, and not those animals and plants that are carbon-based on the surface. Each year, about 50,000 new organic compounds are made. These are new drugs. These are new scents, new perfumes, new colognes. These are new, energy sources. These are new consumer products, plastics, and so forth. Real quick, I want to show you how to think about carbon in its various forms. You can imagine that if you have an ocean, or even the soil, if you go out to, say, Kansas or to Texas, you have this oil rig that sits on top. And that's because down below it, it pumps through a pipe 3 different kinds of things. In this first sequence on top, what you'd expect to be on the top level is the gas phase. This gas phase is what we would call natural gas. And what's important about the natural gas is this is really just carbon in its 1 to basically 4 carbon kinds of chains. So methane, ethane, propane, butane, all good examples of gases in this kind of area. Beneath that gas region is a liquid region. It's going to be a little bit more dense, a little bit more put together. This is what we would call crude oil. And crude oil accounts for really 5 carbons to maybe up to, maybe 20 carbons in length. Starting to get very thin fuels in that 5-pentane, hexane, heptane, octane kind of range. Those are a lot of organic solvents. And then as you get closer to 20 carbons, you're getting into more thicker oils, like engine oil or transmission fluid, that kind of thing. In that very bottom area, this is where you're going to find carbon and hydrocarbons as a solid. And in this region, this is what we would call our really thick tar, our coal, a lot of our asphalt kinds of things. This is what happens when you get to be 20 plus carbons in size. That's going to be at the very bottom. So you can imagine that the small things are at the top, the crude oil liquid mixtures in the middle, and then the solids are at the bottom, just based on relative size. So as they pump out the natural gas and use that in homes first, and they can go in and pump out the liquid second, and eventually mine down and get to that solid structure if they need it for various processes and energy sources and so forth. The 3 prettiest kinds of forms, at least the prettiest of all, would be diamond. We talked about that in week 1, chapter 1. Diamond is the prettiest allotrope of carbon, just meaning the elemental form of carbon. This happens to be in the tetrahedral kind of shape, so very unique that it's the strongest when it has the most legs to stand on. So we just covered the shape chapter, and notice this is the kind of wedge here, the kind of dash there we'd expect for tetrahedral. Tetrahedral has that 4 single bond kind of shape that we mentioned previously. As you look at graphite, which is known as a dry lubricant, it's a lubricant because it can have this repulsion between layers, allowing those little sheets to slide past one each other, much like oily, fingers when you put lotion on, or when you squirt WD-40 into a hinge on a door. Those molecules can slide past each other because of the repulsion of those electrons between those sheets of graphite. This is why your pencil lead kind of drags across the paper and leaves a trail. So you can actually crumble up graphite and put it into a door hinge, and it's going to be just like WD-40 in that sense. It's going to have that repulsion to give that hinge an easier movement and less squeak, so to speak. But notice here where we have a steric number of 4, because we have 4 carbon atoms in 4 different directions. Here we have 3 carbon atoms in 3 different directions, and that would be trigonal planar. So very flat, and it shapes what would look like as a triangle there. And that's typical for double bonds. And we even see that here for these spherical structures of fullerenes. These are named after Buckminster, the scientist. So these are Buckminster fullerenes. They're kind of like a soccer ball, almost identical to a soccer ball with their hexagons and pentagon structure. But this is the charcoal that you use in art class, somewhat of the charcoal that you use for cooking and so forth, but it's also in that steric number of 3 when it comes to relative shape. So what makes carbon different is shape. Go figure. This is why we covered shape in the previous chapter, and this is why we're piggybacking this chapter, even though it's chapter 17 right after it. Shape is what makes the world different, and it's what makes carbon very different. Turns out you can take trigonal planar carbon, use a tremendous amount of heat and pressure, so lots of heat, lots of pressure, and make it into that more stable tetrahedral carbon. And this is exactly what you can do with charcoal or even pencil lead. You can take graphite and then you can turn it into diamond synthetically. And this is what we mentioned kind of jokingly early in the semester, that you can turn your grandparents or lost pets into synthetic diamonds by taking their ashes, their carbon dust, and then using high heat, high pressure to make synthetic diamonds, much like coal that's next to volcanic activity. A more recent kind of hybrid category of allotropes of carbon would be nanotubes. These are kind of like carbon micro pills or nano pills. These can be made into fibers, and if these fibers are woven together, they're going to be 100 times stronger than steel, but also 1/6 its weight. So this is that carbon fiber bulletproof vest that you might see in a lot of science fiction kind of movies. A lot of lining of this on armored vehicles. You can also imagine that the strength of this is about 200 times heavier than muscle itself, if this were, say, like an artificial human being or something like that. So very strong because it's carbon atoms attached to carbon atoms. It's through that catenation process that carbon is so strong. You can actually put medicine inside of some of these pills, use radiation to open the capsule kind of as it's depicted here, and then allow that radioactive material to be out near, say, cancer cells and treat cancers with nano pills, so to speak. And that's really carbon in a nutshell. As we start to see hydrocarbons, what's most important here is to realize that carbon is an electronegativity of 2.5. Hydrogen has an electronegativity of 2.1. That difference of 0.4 tells us that these are all of our nonpolar kinds of molecules when we do that subtraction from its absolute value. So this is all of our oils, all of our fuels, these hydrocarbons, typically in that crude oil or that natural gas kind of phase is where they're typically found. Carbon always has 4 bonds, and typically those are always to hydrogen. So we can use this idea to help extrapolate their formulas, and we'll do that a little bit later on. What you'll notice is counting carbons is going to be important. To know that this carbon chain here has 8 carbons is going to make it different from carbon chains that have 7 or 6 or 5, and we'll learn those prefixes, many which are the same from a previous chapter. These petroleum products are found everywhere. If you listen to the news, it seems like they're only found in gasoline because that's what drives gasoline prices to, higher values. But the reality is probably less than 10% of all barrels of crude oil get turned into gasoline. They get turned into lots of plastics, whether it's a plastic bottle to hold your water, to hold your soda, to hold all your papers in your binder, to hold your cell phone in a case. All of those plastics are also from crude oil. All of our colognes and perfumes and aftershaves, all of our polyester clothing, all of our spandex kind of clothing, all of those athletic jerseys and athletic wear, all of that comes from crude oil. Pretty obvious that the gasoline and the oil in your car comes from crude oil, but it's also the vinyl interiors. It's also the nylon belts in the tires. It's the rubber of the tires. It's the plastic of the bumpers. All of those materials that aren't metal, those are coming from crude oil too. Not to mention all the paint that we put on the surface of those metals, all of the detergents that we clean our cars, that we clean our bodies with, that we can clean our clothes with, all from crude oil. And then even medicines, a lot of their precursors come from crude oil. So even though all we hear about is crude oil is bad because fuel prices are high, the reality is that's a small percentage of actual crude oil. There's lots of other consumer products that come from crude oil. They just don't talk about those because then they can't paint those companies as villains like they tend to do. One of the major differences of organic compounds is their ability to be saturated. Saturated just means that they have the maximum number of hydrogens attached. Anytime you have the maximum number of hydrogens attached, what that really means is you're going to have all single bonds. And what we deal with in chemistry, in the introchem sense, is things that are in chains. We're not really dealing with rings in this chapter much at all, other than for arene specifically, which is a type of unsaturated hydrocarbon coming up. Unsaturated just means you've lost some hydrogens. The easiest way to lose hydrogens is to share with carbon more in a double or a triple bond. So if you're bonding to carbon, you're not bonding to hydrogen. And that's what happens for double and triple bonds when they bond to carbon twice or bond to carbon 3 times. That's at the expense of hydrogen atoms. So in a sense, every time you add a multiple bond, notice you're losing 2 hydrogens for that to happen. You're going to lose 2 hydrogens for that to happen. So as you become more and more unsaturated, you're just losing hydrogen atoms at the expense of sharing more electrons to carbon atoms. And that's the reality of saturated and unsaturated. One of the most common sources for saturated and unsaturated ideas or definitions are from fats, and we'll learn about this more in our lipids portion of our next chapter. But notice the major difference here is your fat that is saturated. So this would be like your Crisco's, your lards, your butters, those fats around steak and so forth. Notice all of these are single bonds. All those little zigzags represent single bonds. But as we get to unsaturated fats, now they can't stack as nicely because sometimes there's a mismatch in that shape and that bond length. So if they can't stack on each other very well, they can't be solids very well. So this is where you get into more things that are oils and less that are fats if they're saturated. So in a separate video, we're going to show you a little bit about saturated hydrocarbons and then get into a little bit of their naming. So we'll catch you then.